Hey, everybody, welcome to AWS On Air. My name's Chad Lacey. I'm a global sales strategist, and I'm joined with my good friend Jordan Sullivan. Jordan, why don't you introduce yourself real quick?
Hey everybody, I am Jordan. I'm a developer advocate on the Amazon Braket team, which is the AWS quantum computing service.
And you guys have got a lot going on over there, don't you? Like,
We do. We seem to have back-to-back launches every week. But this week we have, or actually, I think it launched a couple weeks ago, but now we have a new device, a new quantum device on the Bracket service from our partner Xanadu, which is a Canadian hardware startup that is trying to build a quantum computer out of light. So they're a photonic quantum computing company, and now you can access their device called Borealis. And we're going to get into a bit more details about that
that's super
soon.
cool. So, you and I were talking just before we started the show, right? A lot going on with quantum computing, a lot of changes. Everybody's like jumping in, getting excited about it. But you said something that I thought was interesting around quantum advantage. Can you explain to me a little bit more about what that is?
Yeah, absolutely. So, quantum advantage is a term that's a bit loosely defined, but basically it means that we've reached a point in the development of quantum computers. So, it's a technical and technological milestone. We've reached a point in the development of quantum computers where a quantum computer that's programmable can outperform a classical computer, so a traditional computer, the ones that we're used to, on a scale where to do it classically would be infeasible by some definition. So essentially, it's a point where quantum computers are better than classical computers in a very substantial way. So the first kind of claim for quantum advantage was a few years ago, and initially they claimed that an experiment that they did on a quantum computer would take like 10,000 years on a classical computer. And later, those sorts of claims were a little bit debated, but this is the sort of thing that we're talking about, this really massive timescale difference in how long it would take to run a particular application.
Yeah, and you were explaining to me before is like some of the conversations around quantum advantage. When you say traditional computers, we're even talking about large supercomputers, correct?
Yeah, we're not talking about compared to your laptop, for instance. We're
Right.
talking about compared to, Oak Ridge, like just like massive supercomputers.
Yeah, yeah. So Xanadu announced something here recently. Tell me a
Mhm.
little bit more about that.
Yeah, so Xanadu has actually published a paper in Nature, which is they are demonstrating or claiming to have demonstrated quantum advantage on their device on Borealis. And the specific task that they have claimed quantum advantage for is called Gaussian boson sampling. And essentially, it's a bit technical, the details, but the basic idea is that the problem that's hard for classical computers is keeping track of an exponential amount of information in the number of particles that are in your particular system. And this is actually the reason that quantum computers were originally proposed as an idea by Feynman in like the 80s. The point is that quantum states and quantum mechanics is really, really hard to model because the number of interactions that you need to keep track of scale exponentially with the number of particles in the system. And so when you try to keep track of a lot of these sorts of correlations, it just blows up the amount of memory that you need in your computer. So there is this problem, Gaussian boson sampling, which essentially amounts to either simulating or creating in reality a quantum state where there are a sizable number of particles involved, and we entangle them all together and then measure out the results in a particular basis. So it's actually the measurement step that is hard to do classically because the statistics that you get out of your measurement are determined by the way in which you have entangled all of these many quantum particles, or in this case, they're actually quantum modes. They're modes of light.
Yeah.
It's a bit different, but they're quantum states. So the way in which you've entangled all of your quantum states together, when you measure them out, there are really non-trivial and complex correlations that if you were trying to simulate this, do it on a classical computer, it would just be completely infeasible to do classically. That's the claim. So that is Gaussian boson sampling, and don't worry if it takes you a few tries to get this in your head. It's complicated stuff. It's literally quantum physics. So
So
yeah,
if I understand, and I'm just kind of paring it down for myself, the goal here to reach quantum advantage is we're trying to do something that's super difficult for even a supercomputer to do in a feasible amount of time, right? That a quantum computer is claiming that they can do in a feasible amount of time.
right.
And what Xanadu's releasing in Borealis, as you described, was a photonic quantum processing unit.
Mhm,
So I'm assuming that means it's using light,
mhm.
right? Okay, which is just super cool to me, by the way.
Yeah.
That makes it even more interesting that we're doing processing via light now. Um, so, given what Xanadu's announced and in relationship with AWS, trying to tie this all back together, what what advantage do we have now with this quantum advantage experiment that's different than what we were doing before?
Yeah, so kind of how is this quantum advantage experiment different than previous ones? So
Previous ones, yeah.
it's not the first to have claimed quantum advantage. The main difference is that this is the first publicly available device that has claimed quantum advantage. So in the past, labs have essentially used their own hardware to test their experiments, and you wouldn't have access to that hardware unless you were contracted with that lab. If you were an academic who was doing a collaboration with them,
Mhm.
it's not in general accessible to the general public and not easily accessible in most cases unless you were physically at the location of all of the hardware and the lab. So, what's cool about this device and the launch is that it's actually available on AWS. You can access this as a resource. It has an ARN. You can access it just like you would any other AWS resource, and so you can actually run the quantum advantage experiment yourself. Anybody with an AWS account can do that.
So we're democratizing this to a lot of scientists and engineers to be able to run these experiments on their own as
Hmm.
long as they have an AWS account. Now they have access to it.
Yep, exactly.
That sounds super cool.
Hmm.
So can we see it? Do you have a demo?
Yeah, definitely have a demo.
Cool.
Okay, let me just pull this up. Just going to walk through a pretty brief notebook on how this works. And actually, I think we got a little bit of time, so I will go and start here. So this is actually a diagram of what the Borealis device looks like. So it's sort of a photonic circuit description. And what we're seeing here is it's actually sort of a single waveguide. And so waveguide is just kind of like how you print a wire on an electronic circuit board. You
Mhm.
you print waveguides on photonic circuit boards because you are directing light instead of directing electrons. So what you have here is these three loops, and the way that these are laid out and the parameters on these gates that the photons in the Q modes, as they call them, which are the continuous variable photonic equivalent of qubits, which is the more known term. Uh, but essentially, it's just another way of encoding information into a quantum system. Um, the gates are what are operating on the Q modes. And so what this is depicting is that a Q mode would go through here. It goes through these couple of gates, and then you have a beam splitter, which will send part of the light down this way and part of the light through this delay. And the way that these delays are set up is so that they will sort of entangle, well, they will literally entangle with the Q modes that are coming through this portion of the waveguide. So essentially, if you imagine we kind of send out a pulse
Hmm.
of light, part of it goes forward and part of it goes through this loop. Then we send out another pulse of light so that when this first pulse is finishing going through this loop, it is arriving at this gate at the exact same time as this second pulse is arriving. So they get entangled together. And so
Gotcha.
you kind of just keep doing this. And they do this for 216 separate Q modes. And so they entangle them all together by doing this time delay multiplexing, is what they call it. So it's a way to entangle by using essentially a single waveguide with several loops of delay.
Hmm.
So this is kind of saving you from having to have 216 individual lasers to entangle your light together. You can essentially just use pulses of light and then wait and entangle them with another pulse of light.
Yeah.
And then over here, this is depicting a measurement of the state overall.
Okay.
So what we'll do here for our demo is, first of all, just import our libraries here. So Strawberry Fields is the name of the library that Xanadu uses to interact with the Borealis device.
Okay.
And so it's a fun fact about Xanadu, all of their libraries and stuff are named after Beatles songs. So their quantum machine learning library is called Penny Lane, and their like lower level engine is called Blackbird, and they've got a bunch of really fun things like this. So
You got
Strawberry
to keep
Fields,
it fun, right?
yeah, of course, you gotta keep things light. So Strawberry Fields is Xanadu's library. NumPy is obvious. Then we have this Braket Strawberry Fields plugin, which allows the way of interacting with the Xanadu devices to communicate with the Amazon Braket SDK and API. And then, like I said, the Xanadu device, Borealis, has its own ARN, its own Amazon resource name, and you can specify this by using this Braket engine. And so here we will import a couple of helpful functions. And the way that this works is that you can either manually program all of these particular gates and change the parameters. So for instance, the beam splitter, it essentially sends part of the light one way and part of the light the other way. So part here and part this way. So how much of that gets reflected and how much of it gets transmitted is called a reflectivity. So you can program that. And this R gate, it's a rotation gate. So you're rotating a quantum state, which sounds weird. Like, what does that mean? Essentially, it is, I think the way that they typically talk about this is with what's called the Bloch sphere. So uh, what you see is that in qubits, or in this case it's Q modes, but we'll just stick with qubits, instead of just having, like in binary, a 1 or a 0, you can also have a superposition of 1 and 0. And the way that we represent this is with an arrow pointing somewhere along the surface of this sphere. Up here is 0, and down here is 1. So a rotation is actually bringing the quantum state either along the z-axis or the x or y-axis. So
Mhm.
that's the r. That's where the rotation comes from. Um, so go ahead.
No,
Oh,
I'm with you.
okay, great. Um, so here we're defining the delays. And again, in the diagram, that's telling us how long these uh, loops
Loops
will
are, yeah.
delay the Q modes. And then we can really just enter the device that we want to use, which is this one, the Borealis device, number of Q modes, and there's this squeezing parameter, which I won't get into here. And so it just has to do with the way that the laser light comes out, and the way that you interact with it. Anyway, um, so then to actually construct the circuit that we're going to run on the Borealis device, I'm not going to walk through every single line here, but essentially it is just creating
The different
the
gates.
circuit that is represented in this schematic here.
Yep.
And so you have this S gate, which we saw in the diagram here, then the R gate, the rotation, and then the beam splitter, and then the measurement. And so to actually run this, the Borealis device is not online right now, so this will just continue running. But really, that's all you do in order to reproduce your own quantum advantage experiments, your own nature-worthy quantum advantage experiments, and that's really it.
That's fantastic. So, one question I had is how do people get started using this? I know we mentioned all you need is an AWS account, but
Mhm. Yeah. So as long as you've got your local, well, so what I showed today was doing it from your local development environment. I was just running a Jupyter notebook on my local machine because I have my local environment set up for AWS stuff, so the CLI and the Bato 3, that sort of thing. You can also do it from a Jupyter notebook instance from the AWS console. And if you do that from the Braket console, then you can do these things a little bit more easily because you have all the libraries pre-installed. If you do it on your local development environment, you'll just need to install the Strawberry Fields library and plugin and a few other things to be able to access this. But that is how you get started. And so we have also these examples. Hmm, this one. We have these examples that I will share really quick. This is on GitHub.
okay.
We have photonic quantum computing. This is a folder within the example notebooks. So the tutorial that I was showing is this Borealis quick start,
Mhm.
and the diagram was from this operating Borealis beginner tutorial. So that one has a lot more background and description of the theory and the experiment, so more details.
Very cool. Well,
Mhm.
this is super exciting, and I don't really know that much about quantum computing, but I'm like super excited about it. I think this, it's great that, like I said, we're democratizing this down to anybody with an AWS account who wants to um, try or play around and improve the quantum advantage. So I appreciate you sharing this with us, Jordan.
Yeah, absolutely. Yeah, thanks for having me.
Great, and we will have more to come on AWS on air. Thanks for joining us.